Thank you, Alex. Okay, so we are recording now. Thanks. I hope you had a good spring break last Wednesday. And actually, I joined in and there were a couple of students, and then we realized that it's actually a break. So we canceled class and we'll pick up from where we left last Monday. Okay. Thanks, Anthony, for also turning on the video. It helps, believe me. Okay, so it's a very important class today in the sense that if you pick up what we talk about today, you open your unlock doors to many, many interesting algorithms and applications. Okay, so I'm glad you came today. And of course, I know some people are looking at the lectures offline. Okay, so let's dive in. Any questions at this point from anything else previously? Also, I just uploaded 10 minutes back a new version of the pre-notes, pre-HMM2. So if you've, please download the current version if you're downloading it on your iPad or wherever, whatever you're doing. Of course, it's a small change, but even if you don't download, it's not a big deal. But if you download that, that's good. Yeah. Good morning, Lucas. Yes. Okay, so let's dive in. Quickly, a recap of hidden Markov models that we started talking about on last Monday. So our goal, what was our goal? Our goal was, look, IMU dead reckoning is going to diverge for sure. We cannot keep it constrained, like it's the blind person who's trying to walk in a straight line. And if his head's ability to understand acceleration and direction, even if it is a little bit distorted, there is no way that that blind person will walk the straight line. Over time, the blind person's trajectory will diverge. Right? That's the necessity, which is the mother of hidden Markov models invention, as far as we are concerned. Hidden Markov models were invented for something else, but for us, that's the problem we really need to solve. And so we modeled this problem where we said, look, here is a person walking over L1, L2, L3 till LR, actually. We should have said LR here. And y-axis is time. And at every time, there's a measurement. In our case, it's an IMU measurement. And so you can think of the person's state, the user's state, as at time t1, the user can be anywhere among all these locations, right? At time t2, the user can be anywhere among all these locations. And based on the measurement might say the user is over here at time t1, right? The measurement might say the user is over here at time t2. The measurement might say the user is over here at time t3, and so forth, right? So the measurement is saying something, and you have another source of information, which we call the motion model. We said, look, we have some information that unless we have some additional piece of information, just from the measurements, we won't be able to do much, right? I mean, we can do dead reckoning like we were doing with IMU, but it's going to diverge. If we want to curb the divergence, we need some additional piece of information. And the question and the idea that we have is, we are going to say, does the measurement and this additional piece of information, do they agree? Or to what extent do they agree? Right? Asking this another way, we can say, what is the user's trajectory that agrees the most with the measurement and the model, and this additional information that we have? That trajectory that agrees the most is our best guess of how the user is walking, okay? How the user is moving. So this agreement is very important, right? Which trajectory agrees the most with measurements and motion model? And in this case, motion model is essentially, we have some understanding of how a user walks. In a self-driving car, we have some understanding of how a car drives. The car is not going to drive in a Brownian motion. The user is not going to walk in a Brownian motion. We want to mathematically express the fact that, oh, if a car is going forward, there's a very good chance, very good probability that it'll keep going forward. There's some probability of taking a left turn, some probability of taking a right turn, and a very small probability that the car is going to drive backwards. Right? So we can mathematically model these into what we call a motion model. And now we have the motion model, we have the measurements, and we say, hey, which trajectory agrees with both of them? Right? Or agrees the most with both of them. And we model that as what is called a state transition or state space model. We said the state of the system, the state of the user or the state of the car or the state of the robot goes from state S1 to S2 to S3 till S4, all the way till state Sn, where n is the time index of that state. So S1 means the state of the user at time t1, S2 at time t2, and so forth. Right? So at S1, what are the possible locations that this S1 variable can take? Well, it's all the locations that the user can be at. So S1 takes all these locations. S2 takes all these locations, and so on. And at every state, we have a measurement, M1, M2, M3, all the way till Mn. So a user's trajectory we can think of as going from L1 to L2 to L3. That's one trajectory. Another trajectory could be state 1 is L3, state 2 is L3, state 3 is L3, and it's always L3, and that means the user is static. Okay? That is also a trajectory where the user is not moving. So for every state, the location, the value of that state variable is the same, which is, let's say in this case, L3. Right? So now that we have this variable which can take all these values, hey, that reminds us of a random variable. Right? We do not know which value that variable is taking. It could take many values, and maybe there are probabilities assigned that we could assign to each value because they're not equally likely. So for instance, if a measurement says that S1, or if the measurement M1 says the user is at location L1, then we can say, look, there's a good chance that S1 equals L1. But it may not be deterministic. It may not be for sure because the measurement may have some error in it. Right? So we will now say, you know what? S1 equals L1 with high probability, which comes from the measurement. But it's also possible, I believe, that there is also some probability associated to L2, L3, L4, L5, and so on. Right? So I'm starting to now think of S1 as a probability, as a random variable, and my beliefs are distributed across the possible locations that that random variable can take. And my beliefs will get influenced by the measurements that I get at those states. Right? So we are kind of converging onto this notion of agreement, where we are going to model all of this agreement in terms of probability. And that is why this is called a probabilistic model, and it's also around beliefs. Okay? So we toyed around a little bit with the intuition behind this question of what is PSK given M1 to N. And remember, we said PSK means what is the value of SK? Means, let's say this is SK, means what is the value that this SK random variable is taking given all these measurements M1 through N, means the measurements through time. And we talked about, we discussed how to intuitively think about it, and I hope you have a reasonable understanding that these things are not that complicated. It looks pretty complicated, but it's actually not that complicated in the real world. Especially whenever you feel a little hesitant, think of random variables as a vector. Okay? Where the vector has all the possible values that the random variable can take. And I think things become easy. And if it's a joint random variable, it becomes an n-dimensional space if there are n random variables together. Okay? So that's what we were talking about. Very good. And then we said, let's get one thing, let's look at one value or one expression, which is P probability of S1 through N given M1 through N. Okay. And someone tell me without looking at this reds crossed off, what does this physically mean? Probability of S1 through N given M1 through N. We wrote it down under this scratched part. But what does this physically mean? In English, what would you say? Probability of what?
So sort of your the probability of each trajectory given your measured trajectory?
Yes, the probability of a trajectory, because S1 through N is S1, S2, S3, S4 till Sn, right? And when you're thinking about that, you're saying S1 will take a value, let's say L2, S2 will take a value, let's say L5, S3 will take a value, let's say L3. Now, if you give each random variable a value, that's a trajectory. And you're asking, what is the probability of that trajectory given all the measurements? Now, when you look at this value, you're actually saying probability of all the trajectories, right? This is probability of all the trajectories because S1 through N is an n-dimensional space, right? And every point is one trajectory in that n-dimensional space. Every possible vector in that n-dimensional space is a trajectory. And you're saying, what is the probability of that vector given all these measurements that I have made? It's actually very simple. Okay? And then when we broke this up, it turned out that probability of S1 through N comma M1 through N, that means this trajectory S1 through N and the measurements M1 through N both have happened, that probability turns out to be this. Okay, I said a lot of things. Please ask questions if there are any hesitations, anything that's bugging you, not clear. Good time to ask questions. Guys? Kevin, how fun. Thanks for turning on the video. Utkarsh, thanks as well. I saw you for a little bit. Okay, no questions? Okay. So either you're understanding everything or you're lost and you think that asking a question is not going to help much because you're lagging behind so much. Okay, it feels like one of these two, and I'm hoping it's the former. Okay. All this while, the only thing to remember is PA given B. Actually, this is the only thing we've used thus far. PA given B equals PA comma B divided by PB. Bayes rule. This is all we've used. And maybe we've used another thing, which is sigma over B, PA comma B equals PB. Sorry, equals PA. This is the other thing that we use, which is marginalization, right? Everyone cool with these two? If you're cool with these two, you're in good shape. And this is why I keep telling lots of people that, math, you just there are few pillars, there are few Lego blocks that you need to get right. Everything else is built on top of those Lego blocks, right? At least for engineers, right? For mathematicians, it's very different. But for most of the engineering, real world engineering purposes, there are few Lego blocks that you need to get right. And whatever we are talking about now, I think these two are the important Lego blocks. This one, 1, and this one, 2. Okay, good. Very good. So we have this result and we'll keep it aside. But for now, we have this result. P, the probability of a trajectory and the measurement together is the probability of the measurement given S1 times the probability of S1. Probability of a measurement given S1 is essentially saying, if you are at this location, what is the probability that your measurement would be so-and-so? For example, let's say this is Green Street. Actually, we'll, okay, let me quickly say this, just so that you have that intuition of probability M1 given S1. Let's say this is Green Street. This is university. Right? Let's say someone tells you this person is at Jimmy. Hey, where actually Green Street has changed so much. I don't know which is where. Okay. Busy Bank is still there, right? At that corner of 6th and Green. Is that right? Oh, okay. I think that there's a Busy Bank here somewhere. Or maybe there's a McDonald's here. Let's say this is a McDonald's. Right? There's a McDonald's there, right, guys?
Yeah, there is.
There is. Okay. Right. So let's say I tell you that SK equals McDonald's. Okay. And your measurement says you are here. So now you're going to ask the question, what is the probability that your measurement equals this given your SK equals McDonald? Right? And let's say this measurement is a GPS measurement. So if this value is very large, let's say this value is 20 meters. Then you say, hey, that is unlikely. That probability is very small because the GPS error is typically not 20 meters in Champaign. In Chicago downtown, it might be. In Champaign, 20 meters seems unlikely. Right? So you're going to say this value is small. But if your GPS tells you this is the value, let's call it GPS 1, GPS 2. Let's call this GPS 1. So if you say probability of M1 equals GPS 2 given SK equals McDonald, that probability is large because you know what? This distance is 3 meters and you say, GPS can easily have 3 meters. Right? So this M1 given S1, that's the meaning. Right? How does the measurement agree with the value of the state, that the value of the state that I'm assuming, right? I assumed that the state is as McD. Okay. So this is what M given S means. Oops. Let me just make this small. And P of S1 is the probability of the initial state. Okay. P of S1, S1 equals L1, L2, L3, L4, L5. So you're saying what is the probability? S1 equals L1. What is the probability? S1 equals L2. What is the probability? S1 equals L3 and so on. Okay. That times P of Mi given Si and P of Si given Si minus 1. And remember, P of Si given Si minus 1 came from my transition probability matrix because that's my motion model. I've expressed my motion model as a matrix, and that matrix essentially says if I am at a particular location, what is the probability of going to another location, including that location? If I'm at location Li, what is the probability of going to Lj? So it turns out that this expression is the multiplication of these two. Very good. That's where we stopped last time. Okay. So our real goal is to measure, is to basically come up with this quantity. Can someone give me the English version of this quantity? We think in language. We do not, most of us engineers, we do not think in math, right? We always think in language. So it's always good when you look at a math, when you're trying to understand math, try to say, can I say this in English? So how can we say this in English? What should we think when we see this expression? Probability of?
Is it the probability of my position given all of the measurements I've taken?
My position when?
At, I guess, any time k, but M1 through N is like a Does 1 through n span the entire
Correct. 1 through n
time
spans
measurement?
all the measurements.
Yeah.
Basically,
Mhm.
time goes from 1 to n, right?
Yep.
Now tell me, you're right. Just refine it and say it. This is the probability that my kth state,
Right.
this is the probability of my kth state given all the measurements.
Mhm.
And what is kth state? Where am I at time k?
Yep.
And
Mhm.
sk is obviously going to take all the values possible till lr, right?
Right.
Remember, right? Sk is the random variable, right?
Yep.
So when I say what is the probability of state k, I am actually saying what is the probability of state k equals L1, what is the probability of state k equals L2, probability of state k equals L3, and so forth. Very good. Okay. Now, this sk given m1 to n. So again, let me just reiterate. What is my location in the airport at time tk given Google has all my measurements from time 1 through n, where n is greater than k. Make sense? I walked through the airport. My phone made some measurements. Mine is a Google Android phone. Google took some of those data. Google has all the measurements that I made while I walked through the airport. And now Google's algorithm designer, Google's HMM modeling guy is now asking the question, at the kth time, where was Romit in the airport? That's what this probability is asking. Okay? Very good. Now, if you think of this as probability of A given B, then I can write that as P of AB divided by PB. Oh, now PB is basically this measurement of M1 through N that is already given to me, right? And not only that, I care about only the numerator, PAB, because PB is the same for all possible values of SK. Right? PB doesn't change SK because for all SK equals L1, it's the same PB. SK equals L2, it's the same PB. Right? So I only care about the numerator. So that's why I write this as proportional to SK comma M1 to N. Okay. And then I can write this as SK comma M1 through K comma MK plus 1 through N. That I can easily write, right? No problem. Now this one, I'm going to write that as M of K plus 1 through N given SK comma M1 through K. Right? Now what am I doing? I'm saying P of ABC equals P of C given AB. Right? Chain rule. Now, if this is P of C given AB, this equality doesn't hold. So I need to multiply this with what? Guys, if I need to finish this equation, what do I need to do? Times what?
PAB.
PAB, very good. Now I apply Bayes rule to PAB once again. So I can write this as P of C given AB times P of A given B. How should I finish this then? What is missing? I need to write something more.
P of B.
P of B. Okay, very good. So let's do it exactly that way. I wrote the left-hand side equals, sorry, the left-hand side is this one. Let me write that actually.
Real quick, Professor.
Yeah.
Why is it not P of B given A times P of A?
Yeah, you can do it either way. You can do it
okay.
either way, right?
Okay.
Doesn't matter. So we are going to do one of those ways.
Okay, sure.
So P of k plus 1 through n comma sk m1 through k times we have to write P of sk comma m1 through k. Very good. So P of k plus 1 m of P of mk plus 1 through n. Now observe that this part mk plus 1 through n, once you know sk, it doesn't matter what m1 through k is. This is the Markov assumption again. We are going to say it doesn't matter what m1 through k is, this only depends on sk. So here is what that means physically in English language. Google says once Romit in the airport is at Starbucks, right? Once I know Romit is at Starbucks in the airport, the rest of the k plus 1 through n measurements will only depend on whether Romit is at Starbucks or not, right? The measurements of k plus 1 through n does not depend anymore. Once we know Romit's Starbucks location, those future measurements don't depend anymore on the past measurements. Because the past measurements has only influenced Romit to come to Starbucks. So once I know Romit is in Starbucks, I don't care what the past measurements are. All the future measurements will only be dependent on Romit's SK's location. Right? So I do not care about SK and MK together. I can basically eliminate this and I can write this, that these measurements are only dependent on SK. Okay, very good. And now this one, SKMK, this is probability of AB. I'm going to write that as probability of A given B times probability of B. Right? Very good. Hey, do I care about this one? I don't care about that one because again, remember my left-hand side is saying what is Romit's current or location at TK given all the measurements M1 through N. So whatever the SK value is, it will always have this term as a part of this term. So if I want to find which value of SK has the highest probability, I really don't care about this because all the values of that SK will have this term in it. So if I want to find the max, it will always contribute the same value. So I can forget it. Very good. So then I write this as P of SK given M1 through K times P of MK plus 1 through N given SK. What does that mean? That means I have broken down the problem of where is Romit at time Tk given all the measurements that I got from Romit while he was in the airport. Romit has flown out of the airport now, right? Google has the full measurement until he got into the airplane and just flew out. But from that measurement, Google is saying at some intermediate time, where was Romit? That's the question, right? And that question turns out to be a combination of where was Romit given all the measurements till that point, SK given M1 through K, times what is the probability of the future measurements given this SK. Okay, this is an interesting part where I really want you to focus and get it, right? If it clicks, it'll click for you forever. It's like learning to bike. You learn it once, you never forget. Okay, so this is called forward because this is online. or this is real time. Why is this real time? Because SK given past measurements, I can tell you right now where Romit was. Right? This is called backward. And this has to be done offline. Right? Google, only because Google has my future data, it can do better estimate of where I was at SK because it has data all the way till N. Okay? So this is why this part is the offline. If Google wanted to track me in real time in the airport, Google does not have this part. Right? This is only the real time tracking part. Right? But right now we are asking the question, how can we best localize Romit with full data, meaning offline? I hope that is clear. Very good. So just to make sure we get this perfectly, right? This part is not difficult, but this part is a little bit tricky. Here is an analogy. Okay. Suppose you are a cop and there's a murder suspect who is out in the wild. And you have surveillance cameras that are spotting this car of the murder suspect that's going around in Champaign-Urbana. Right? And you are trying to say, where is the murder suspect right now so I can dispatch back up to that location, wherever he's likely to be right now. This is also a dead reckoning problem, right? You've gotten to see the murder suspect's car from some surveillance cameras at some time points in the past, and you're trying to figure out where is the murder suspect likely to be at this time. Okay. So, or where was the murder suspect at the time of the murder? Maybe that's the other question, because you have data from surveillance cameras for the whole day and the murder happened at 3 p.m. That's weird because it's happening in broad daylight. But anyway, okay. So you're now trying to figure out, is this guy, was he at the murder location at 3 p.m. or not, based on all the surveillance camera pictures that you have from 8 a.m. to night 10 p.m. So SK is that 3 p.m. Okay. So then you're basically, now you're broken down the problem into probability that murder suspect is at SK equals Green Street. Suppose the murder happened at Green. Right? Probability that the murder suspect is at SK equals Green Street, given K equals 4 recent surveillance camera measurements of Main Street, Wright Street, 6th Street, University Avenue. So what are you saying? You know murder happened at Green Street. That's SK. You're saying, what is the probability that this car was at SK, Green Street, given that the past measurements that I saw, the past 4 measurements that I saw are Main Street, Wright Street, 6th Street, University. This probability looks high, right? Because the car could have driven from Main Street into Wright Street, then went to 6th Street and then came to University Avenue. This probability looks pretty high. Right? Then you're saying, you know what? Seems like this guy could be the murderer. Right? Because this measurement looks pretty good. If this measurement is in agreement with the murder location. But then you said, wait. You also need to look at the rest of the measurements, right? So then this measurement says probability that 4th to 8th measurements are Neal Street, Kirby Road, Lincoln Drive, University Avenue. Those are the following measurements given suspects kth time location is Green Street. That looks weird because from the kth time to the k plus 1th time, he drove from Green Street to Neal Street very quickly. And then he went to Kirby Road and Lincoln. It seems like he's far from the murder location, which gives you some pause that, hey, this probability looks small. Because if he was at Green Street at SK, it's very unlikely that in the next time step he would be at Neil, and in the next time step he would be at Kirby. Maybe these measurements are wrong, or maybe he was not really at Green Street at that time.
I just have a quick question about this.
Yes.
It seems that Neil Street, Kirby, Lincoln, all of these appear to be SKs, right?
No.
Rather-
These are your measurements, because these are your surveillance camera measurements.
Okay. But then aren't the states similar in this case as well? Because
Yeah.
states could also be so.
Yeah. So basically, I'm saying that imagine the measurements are GPS locations from 1 through K. If you think of that as measurements, and if you think of SK as also locations, so this is a case where the measurement space and the location SK space is the same, right? If you take another measurement where the measurements are IMU, then that IMU space and the SK space is not the same. Right? So I'm giving you an example over here of this murder where the measurement space and the SK space is the same.
So this sort of shows you can always do this with just the first probability, but is kind of the intuition behind this. This is kind of showing why offline tracking is always more accurate.
Correct. Exactly. You can do this from the first one, but you might make mistakes just from the real-time online one. Offline will make it better. Right? Here is another quick example. Suppose I tell you the sequence of grades that a child has gotten from grade 1 to grade 10th. Okay. And now I say, yeah, let's say grade 1 to grade 10th, and SK is the intermediate point, let's say grade 6, 6th grade. Okay. And now I tell you probability of SK equals UIUC, because UIUC needs top grades to come to UIUC. SK equals UIUC given grades 1 to 6. Right? This is a real-time tracking. I tell you the grades for grade 1 to 6. Now tell me what is the probability that this guy came to UIUC. You have some understanding, right? This guy did very well from 1 to 6. There's a good chance of him coming to UIUC. This guy didn't do very well from 1 to 6. This guy couldn't have come to UIUC. But let's take a guy who didn't do very well from 1 to 6, but just was stellar from 7th to 10th or 7th to 12th. Hey, then your estimate would change, right? If I told you just the grades 1 to 6, and if grades 1 to 6 was not too good, you would say this probability is low. But now if I told you P of SK equals UIUC given grades 1 to 6, and grades 1 to 6 is not too good, times probability of grades 6th to 12th given SK equals UIUC, this grade 6 to 12, suppose is stellar. Then you can say, oh man, whatever this low value is over here, it gets compensated by this high value. Then you say, no, it's very much possible he came to UIUC. Does that make sense? So
or even like his grad grade, his grad school grades, because
yeah, that's the future.
Kind of.
Actually, that might be right. If I give you his grad school grade, actually, you're right.
Gotcha. Okay.
Huh?
I said, okay, that makes sense.
Yes. Actually, what I should do is, you are right, because we want the n to be greater than k. So let's say this is grade 1 to 12. and this is also grade 1 to 12, and then grades 13 to 17, meaning your college grades, right? And SK is got admission to UIUC. 13 to 17 is your freshman to senior in your college, right? So now if I give you the college grades, then you say, this guy is stellar. There's a good chance he came to UIUC, right? So your estimate of SK equals UIUC improves once you know this information. Otherwise, the best you can do is this information. Does that make sense, guys?
I have a question.
Yes.
So in the very first line, you have P M1 to K.
Mhm.
Are we just throwing that away, or
we aren't throwing that away. We are just not, we don't need to use that, because all values of SK will have that in it, right? These are basically the grades,
okay?
right? Your SK is equals to UIUC, MIT, Princeton, right? So on.
So
That's what SK is. And you want to figure out what is the right value of SK.
Okay, so
For that, your P of M1 to K is grades from 1 to 12. You don't care, because whatever the value is, UIUC, MIT, Princeton, blah, 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 these grades will remain the same. So in this whole expression, you don't really care about this value, because this value is constant for all values of SK.
Okay.
Very good. Okay. So this is the backward offline version. Okay. Very good. So if that is clear, actually I had this one where I wanted to say something where, so let's say this is the state space and M1 through K tells you this. Let's say these pink ones are your measurements. Your measurement is saying at time T1, the user was at L3. At time T2, the user was at L5, and so forth. Okay, let's actually make it a little bit easier, so maybe I'll be able to make my point. Time T2, the user was at LR minus 1. Actually, let's make it even easier. Let's call it L10. 4, L4, L5, L6, L7, L8, L9, L10. Very good. So measurement M1 equals L3, M2 equals L9, M3 equals L4, L5, M4 equals L6, and M5 equals L7. And let's say that the motion model says that there's a very good probability. There's a very high probability that the user keeps walking in the same direction as it was walking the last time itself. Right? What can you say from this situation? What can you say about the measurements? Can you say anything about the measurements that were taken?
Perhaps measurement 2 might have been erroneous. If
measurement 2 might have been erroneous, right? Because from your other measurements, the other measurements are agreeing with the motion model as well, right? So you can kind of say, this must be a very low probability event that the user was here while the measurement was here. So you see, you are saying that, look, I don't know where the user is in the beginning. The user can be here, the user can be here, 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 here. So in the beginning, given that my measurement is saying this, maybe my probability of where the user is like a Gaussian around here. Right? At 3, the probability is high at location 3, but in other places there is some probability. At time t2, you're saying, okay, if you just take time t2 into account, L9 has a very high probability. But look, my motion model says that if the user is at location L3 at time t1, it is very unlikely that it shot like a rocket to L9 at time t2. So then you say, okay, maybe the user was somewhere here then. Because you're trying to say, what is the location at time t2 which reasonably agrees with my measurement and my motion model? Okay? And then you say, okay, at time t3, the user is over here. That means it's very likely that it's like this, because time t3 again agrees very well with my motion model and the measurement. T4 also agrees very well. T5 also agrees very well. So your final trajectory would look like, right? Why this bump? This bump was because you cannot completely distrust the measurement, but you also have realized that, you know what, it's not likely because rest of the things are pointing towards this trajectory. And that gets reflected mathematically. You have this bump, but that's how you do it, right? So your measurement is pulling you in the wrong direction, but you're not getting completely pulled, but you're not eliminating that either. It's not an outlier detection either, because hey, if it so happened that this guy had to rush to the hospital, then come back or something happened, emergency, that's why your trajectory turns out to be that. Okay. So you're trying to find the trajectory that is in both agreement with the motion model and with the measurement. And if the measurement pulls you too far away, the motion model is pulling you back. If the motion model pulls you too far away, the measurements are pulling you back. Questions, guys? Okay, good. Okay, so now let's get into math, because if you have that clear in your head, the math will flow very smooth. Okay. Now let's look at the forward component, which is PSK given M1 through K. One second, guys. Give me 1 second. My notes here. Okay, good. Okay. So you're cool with this, right? We now want this forward component. Earlier we had all the way till n. We saw that as the forward component and the backward component. Now we are focusing only on the forward component, and then we'll focus on the backward component, and we'll put it together to get this. So the forward component is Sk given M1 through K. Okay. Anytime you see Sk given A comma A given B, you can think of it A probability of AB divided by PB. That is only proportional to probability of AB. Again, same thing. Because the only thing we care about is Sk equals L1, L2. That's the real thing we are after. And for that, all these values, all these denominator values are the same. So now this right-hand side, this one, we can write that as we are going to do marginalization. By marginalizing, we can write this as, if I sum over sk minus 1. Someone quickly tell me what is inside here. I take this, but I sum over sk minus 1. So then that is psk, comma, sk minus 1, comma, m1 through k. Make sense? PAB, sum over B equals PA. Very good. Now, what I do is I separate out MK from this, from here, and I write MK given SK, SK minus 1, M1 through K minus 1. I just took MK out and now I conditioned on the rest of it. If I did this, then I also need PAB equals PA given B times PB. So I now need PSK, comma, SK minus 1, comma, M1 through K minus 1. Okay, very good. And this summation stays. Good. Now look, MK given SK, SK minus 1, M1 to K minus 1, does MK, which one does MK depend on? Someone? The measurement at MK, once you know the SK, you don't care about SK minus 1, you don't care about the past measurements anymore. You only care about the measurement, you only care about the state SK. Why? Because the measurement at a state does not depend on the past states. Do you have an intuition about this? This is what is called the Markovian assumption, right? I want to give you an intuition very quickly as an analogy. You are a statistician at Zurich airport, okay? And a lot of tourists are coming to Switzerland, okay? And you have a job of figuring out, or you are trying to estimate who will go to which tourist destination in Switzerland, right? You have two possibilities. You can say, once a person lands onto Zurich, then the probability of where they are going to go is a function of the fact that they've landed at Zurich. It doesn't matter where they came from, right? So you say, my estimate of what this person is going to do is only a function of the fact that that person has landed at Zurich. And maybe you're a statistician, your estimate of what a person would do in let's say London is a function of whether the person has landed in London or not. You do not care if the person came from US to Zurich or Canada to Zurich or India to Zurich or China to Zurich. That you don't care about. You make your estimations only on the fact that this passenger has landed at Zurich. Therefore, his interests might be at looking at Alp mountains. You are not taking into consideration the fact that he has landed at Zurich and that he comes from Iceland might mean so and so. You're not taking that into account. You could potentially, but you're saying, I'm only going to base my judgment based on the fact that he's landed at Zurich. He or she has landed at Zurich. Okay? So where he came from doesn't matter. Similarly, SK minus 1 doesn't matter. My measurement is only a function of SK. Actually, this is true for GPS, right? When you take a measurement of GPS, does GPS care about where you came from to that location? GPS will only make a measurement for that location based on triangulation at that location. It doesn't care about the past. Right? Very good. So MK given SK times Now you have to look at this part. Sk given, now I'm again doing the same PAB. Sk given Sk minus 1, comma, M1 through K minus 1. And because I did that, I again need to multiply and make this Sk minus 1, M1 through K minus 1. Right? Very good. This stays as is. Someone tell me this. This again becomes Sk given Sk minus 1. What is my value of Sk is a function of where I was last. Doesn't matter what the previous measurements were. If I know where I was last, that's all I need. If I did not know this, then Sk might depend on that. Right? Another way of thinking about it is this one only influences this one. Once I know this one, I have all the information captured in Sk minus 1. Because M1 through K minus 1 influenced Sk minus 1. And once I have Sk minus 1, I don't care about all of that. Sk only depends on Sk minus 1. Right? I see that you've come first in your class in 10th standard. Once I know that, I don't care. I was going to say whether you smoked pot, but I decided not to say it. Well, I still said it. But then I don't care what you did before your 10th standard. Right? Whether you played basketball, whether you spent your all nights watching movies, I don't care. I don't need those measurements anymore. Because I know now that you've come first in class in your 10th grade, that's all. That's what I'm going to use to predict how well you're going to do in college. Right? Same thing. And then this stays the same. Very good. And all of this, remember this sum, this is over the sum because I'm evaluating this part that is inside the sum. Very good. Does someone see anything nice in this expression? Does someone see any pattern, similarity, self-similarity? Right? Let's call this alpha k. Then what is this?
Alpha k minus 1.
Perfect. Okay. So now I have alpha k equals this times alpha k minus 1. Right? Look, what was my original problem? The biggest problem we are facing is the user can be here. For every probability, for every possible location, I have to say, if the user was here, what is the chance that the user is here? What is the chance that the user is here? What is the chance that the user is here? And so forth. But that's only part of it. If the user was here, then what is the chance the user is here? What is the chance the user is here? What is the chance the user is here? And so forth. Sorry. So you see, right? It's a brute force kind of a process because we want to take every information into account. If the user was here, what is the probability the user is here? If the user was here, what is the probability user here is here, right? And then you have to do the next one. If the user was here, and then if the user was here, what is the probability the user is here? It's exponential, right? The state space, the space of probability is growing exponentially. That's the difficult part. And we are trying to say, among all these exponential possibilities, which trajectory is the most likely? You can do this brute force because you know measurement given state, you know all the sk given sk minus 1. You can do this whole thing in a brute force manner. But that would just blow up your compute. Hey, but it turned out that you have this self-similarity. It's a recurrence relation, and therefore you can do dynamic program. Right? That makes, right? I hope you've seen dynamic programming. If you've not seen dynamic programming, maybe it's still okay. All we are trying to say is once we've computed some part of the state space, we don't have to recompute it. We are going to reuse it, and that will cut down computation logarithmically. Okay? That's the valuable part here. Okay? But there's one more thing we need to work on, which is, hey, where do we start this dynamic program? The starting point is alpha 1. So what is alpha 1, guys? What is the expression for alpha 1? There is no sk minus 1 for alpha 1, right? So alpha 1 is p m1 given s1 times p s1, because there's no sk minus 1, right? Does that make sense? So this is saying initially, where were you? What is the probability? And what is the measurement error initially? Okay, very good. So if you think about this, this becomes P of M1 S1 divided by P of S1 multiplied by P of S1. So that becomes only P of M1 S1. Okay, let me write this out just for clarity's sake. This is equal to P of M1 S1, basically a comma here, divided by P of S1 times P of S1. Make sense? So I need to now compute what is the initial condition P of S1 M1. Oh, I see. Okay. So this is basically, simply P of M1 given S1 times P of S1. This needs to be known. And okay, let me just say that once again. Guys, alpha k is this. So alpha 1 equals P of, this is sk m1 through k. So this is s1 comma m1 through 1, which is probability of s1 m1. Forget what I said just 1 minute back. Right? That is what alpha k is. Right? So now this I can write that as this. Did I confuse you? I hope I didn't. This is alpha k, which means alpha 1 is this. M1 through 1 is M1. And that PAB is PA given B times PB, that is this. So then this is probability of S1, right? If you know that Romit entered, if Google knows that Romit entered the airport through this entrance, then you can say probability of S1 equals entrance equals 1, S1 equals Starbucks equals 0, everything else can be 0. Then that means you know that the entrance was at that location. But in some other cases, you might know where the person started. Right? You don't know which entrance he came from. Then you can say, let's make it equal probability. Perhaps all locations have equal probability. Right? So PS1 equals 1 by R, because there are R locations, LR, right? Remember L1, L2, L3, LR. So this is also one way of doing it. So if you don't have any information, make them all equal. Now, what is M1 given S1? This is what you get from your sensor data. Errors of sensors from data sheet. Right? So for example, like I told you, right? If I tell you that you are at ECEB, the ECEB building, and your GPS says this is your location with some distance 3 meters, what is the probability that the GPS is right? Right? Or what probability with what probability will GPS give you 3 meters error? Right? And that typically there will be a distribution that the GPS chipset will give you. The distribution looks like this. Right? At 3 meters, your probability is this much. Right? 10 meters, GPS would say very, very low probability that your GPS is going to give you 10 meters of error. Okay? So from this graph, you can figure out what is M1 given S1. Make sense? Very good. That means you have everything you need. You start off with alpha 1, you calculate alpha 2, alpha 3, alpha 4, alpha k, and you have gotten the online version, the forward version. Please ask me questions.
I have a question about dynamic programming here. Like
Programming?
yeah,
Dynamic
although
programming.
like the time complexity has reduced to polynomial, suppose like the state space is of dimension n and we have k, and then it will reduce it to big O of n times k, right? But the thing is here, the n is like infinite, since we can have like 1 meters state space, 10 meters, 100 meters low.
That's right.
So it's like the complexity is still infinite. How
That's
do you
right.
deal with that?
That's right, Jiahong. Jiahong, that's very true. N is very large,
Yes.
right? And K would also go through N. So hidden Markov models are better, of course, than brute force. But hidden Markov models will still have pretty strong, pretty high complexity, pretty high computational effort is still pretty high. And it's a function of what granularity you want your location to be.
Yeah, yeah. And
Exactly.
also like the space, the state space, it has to be like finite, right?
Correct. It has
Otherwise
to be finite. Basically, you have to chop it up, right? So you know that state 1 to state 2, it's not continuous. Okay. If it becomes continuous, there are modifications to hidden Markov models where you can make it continuous and you can do things. But you're absolutely right. Hidden Markov model is still a pretty heavy, CPU heavy approach. But the important point over here is it is optimal, meaning you have used every piece of information that you have in estimating at the expense of a high cost still. And when I say high cost, it's like high cost compared to an efficient algorithm, but compared to a brute force, it is much better.
Yeah, I agree. Like, do you have any algorithm to speed up the?
Absolutely, absolutely. This is where there's a lot of work that has happened, and we don't have. Maybe I will design another course. I'll offer a new course, which will be this follow-up from here.
Mhm.
And there we'll talk about Kalman filters, particle filters, all kinds of other filters, which are based on hidden Markov models that will actually reduce your complexity. And you even have a parameter that will tune how much complexity you want.
Ah, that's cool.
Yeah. Very good. Okay. Any other questions, guys? I know this looks scary, and in a paper, it'll look even more scary. If you read a paper or if you read an article with math, it'll just look scary. Okay. But it's not. It's not at all scary, right? You just need to get M1, M2, probability of M1, M2, M3, M4 till Mn is an n-dimensional vector. That's all. Right? You have to just think of it in that way. Very good. Shall we do the backward? Let's do the backward. So now what is the backward part? Ooh. 1 second. Okay, keep thinking. If you have questions, and I should be ready in a minute. Guys, questions? Good. Okay. Let's now talk about the backward part. So what is the backward part? Backward part is mk plus 1 to n given sk. Does that make sense? Right? Remember, right? This is where we were. This is backward. Google is asking, what is the probability of all these measurements that I've received given Romit is at Starbucks? This is a posterior or a likelihood? Jiahang, this is posterior. Anyone else?
Likelihood.
Likelihood, posterior. Can someone tell me why is this a likelihood?
Because SK includes all the possible states.
Because SK includes all the possible states. SK is the hypothesis. Very good. Jahang, does that make sense that this is actually likelihood?
Yeah, it makes sense.
Good. Okay. Good. So we are now looking at, hey, by the way, what was this? The forward part?
Posterior.
Posterior. Okay, very good. Now you're getting into the groove.
Yeah.
So this is the likelihood, and let's look at the expression now. P of k plus 1 to n given sk can be written as P of AB product divided by P of, guys, you tell me now, what is the denominator?
Is it SK?
Very good. Can we ignore the denominator? Can we? No, we cannot ignore it anymore. Right? Because my left-hand side, for every sk, this denominator will change. For every value of sk, this denominator will change. So how can I ignore the denominator now? Okay. So I take the denominator 1 by psk and then do sigma of sk plus 1. Again, I'm marginalizing. But I'll do sk plus 1, comma, mk plus 1 to n. I can do that, right? Now I'm going to do the following. I'm going to say mk plus 2 to n given sk, or let's say given mk plus 1, sk plus 1. Any problems? Basically, I took mk plus 1 to n and I divided that into mk plus 1 and mk plus 2 to n. Okay. But once I did that, now I need to have mk plus 1, comma, sk plus 1 here. Make sense? But look, I'm going to write this mk plus 1, comma, sk comma sk plus 1, I'm going to make that mk plus 1 given sk plus 1, and then write sk plus 1 here. Is that okay? Chain rule. ABC, A given BC times BC. Oh, this sk comma sk plus 1, I'm going to write that as sk plus 1 given sk. I'm doing chain rule. Very good. So now this one, mk plus 2 give till n, depends on what, guys? Now you have to tell me. The grades that you measure for this candidate from k plus 2th grade to n depends on which one?
Plus 1.
Sk plus 1, right? That's the only thing that it depends on, because sk plus 1 captures mk plus 1 and sk. So then you write this as m of k plus 2 to n given sk plus 1. Very good. What do you do for this? This is m of k plus 1 given what? What does it depend on? mk plus 1. The GPS measure, the k plus 1th GPS measurement depends on the k plus 1th location or the kth location or both.
Just k plus 1?
Just k plus 1. Right? And times p of sk plus 1 given sk. And now, look, this psk and this psk can cancel off. Right? Because remember, I'm adding only on sk plus 1. Right? Guys, again, I keep want to connect to everything that we've been seeing. When we say sk plus 1, again, papers will write this all the time. What is coming in your mind? How do you think of this addition? This addition is, remember, sk plus 1 is nothing but L1, L2 all the way till LR. Right? So you add this, this becomes sk plus 1 equals L1 mk plus 1 to n plus sk plus 1 equals L2 comma mk plus 1 till n plus. You keep doing this for all values of sk plus 1. That is what it means to sum. Which means your sk is not getting affected at all. Which means you can cancel off this sk and this sk. Let's do that with red. And that is what you have. This is p of mk plus 1 to n given sk. Whew. Anyone sees any pattern?
Well, if you call left-hand side like alpha again, I guess alpha k, I guess.
Beta k.
Then the first term would be beta k plus 1.
Perfect. Okay. So now I have sigma sk plus 1 beta k plus 1 times p of mk plus 1 given sk plus 1 times p I have another dynamic program. right? So I've brought down both of them into a dynamic program. All those exponential possibilities I would have had. Right? BK plus 1 dynamic program. Again, this is nothing but sensor error distribution. What is this, guys? The last one?
Transition matrix.
Perfect. Transition probability matrix. You've gotten the backward part as well. The only thing is, hey, how should we initialize BK, beta K? Right? What is beta 1? Actually, is it beta 1 now? Because
You're
observe
going backwards.
beta K, huh?
Are you going backwards so you count?
I'm going
the
backwards, exactly. Right? So I have to basically start from beta n minus 1. Okay. So look, beta n minus 1, what is it? What do I write beta n minus 1 as? Because I wrote this one as beta k. So tell me what is beta n minus 1?
P of mn given s n minus 1.
Perfect. Good. How do I get that? Now I need to massage. This P n to n is basically m of n to n is basically mn, right? So mn, comma, sn minus 1, comma, sn divided by, what is it divided by, guys? Again, P of A given B is PAB divided by PB. Very good. So now I take PSN minus 1 out because this sum is over Sn. And this becomes PMN given Sn minus 1 times what? Someone? I'm rewriting this. I've taken the denominator out. So forget about the denominator. I'm rewriting the numerator, and I've written this numerator as P of Mn given Sn minus 1. Now what do I need to write here?
P of Sn. I'm sorry. You go ahead.
Sn and then Sn minus 1. Yep.
Perfect. Okay. Now P of Sn comma Sn minus 1. Hey, that I can write as P as Sn given Sn minus 1. And what else do I need to write now?
Probability of Sn minus 1.
Perfect. Does anything cancel?
The probability of Sn minus 1.
So this is Mn given, what should that be? Markov. You only care about candidates coming into Zurich, not from where they flew in. So what is this Mn given?
Just Sn.
Just Sn, excellent. Times Sn times Sn given Sn minus 1. Do you know both now? Both are known. This is your sensor measurement. This is your motion models, probability, transition probability matrix. You're done.
I'm sorry, can I ask a question?
Say that again.
Can I ask a question?
Sure.
I just have I'm really confused about how you get to the summation part. So let's say for beta n minus one,
Mm,
you have that probability. I get
Mm.
that, but how do you get it? How do you transition from probability to the summation of probability?
Sure.
Like, I don't know where that Sn came from.
Sure. Can you see? Let's write this. Sorry. Yeah, actually, that's fine. Let's say P of AB. Can you visualize this? Can you visualize this? How do you visualize this, Jan Hao? Probability of AB, I visualize this as a,
It's like a point.
I would say visualize this as A can take all these values, B can take all these values, and AB means A takes some value, B takes some value, and that is the probability. This value is PAB. Does that make sense? I think
Yes.
all of the confusion starts from here. Jan, how does this make sense?
Yes.
Perfect makes perfect sense, right? In fact, I often tell people, let's say this value is 5, this value is 7. That means this value, which is in this value, is essentially probability PA equals 5, B equals 7. Right? Always think of A as a vector, B as a vector. So PAB is a two-dimensional space. Very good. So now what I want is, I want PA. What does that mean? Remember, A is a vector, which means what I want is P A equals 1, 2, 3, all the way till 5 or till 10. Means I want PA equals 1, PA equals 2, PA equals 3. I want those probabilities. So what I really want is PA equals, let's say I want PA equals 5, which is, this is 5. So that means I want all probabilities where A is 5, which means probability A equals 5 and B equals 0. Probability A equals 5 and B equals 1. Probability A equals 5, B equals 2, and so forth all the way. So basically I want this, I want the area under this curve, or the sum of all the probability masses along that direction. Jian Hao, does that make sense?
Yes.
Very good. So then I can say probability of A is nothing but sigma over B of probability of A comma B. Because look, I'm adding for all values of B.
Okay, I get it now. Thanks.
Get it now? Very good. I am glad that you do not feel shy. Just ask questions, right? You get this, this clicks, everything else will click for this course and many other courses. Very good. So that is how we got this part, S sigma over Sn. And then we have Bn minus 2 sigma of Sn minus, sigma of Sn minus 1, beta n minus 1, P of Mn minus 1 given Sn minus 1 times P of Sn minus 1 given Sn minus 2. You are good to go from here. You can keep building up now. Beautiful. Okay. I really like hidden Markov models, the way it came together. Okay. So recall, originally we wanted Google to find this. That's the offline version. We decomposed that into the forward version, which turned out to be a dynamic program, the backward version, which also turned out to be a dynamic program. Haha. And I have a dynamic program for the forward version a dynamic program for the backward version, and therefore I can estimate what the user, where the user is using all pieces of information. Okay. So HMM is efficiently, and efficiently doesn't mean super efficiently, but much better than exponential growth, efficiently identifying the most likely value of a state or a state variable. Oh yeah, let me write variable here. Of a state variable from a huge space of possibilities. Right? That's called the state space, meaning the space of all trajectories possible. Now you can, now remember over here we are calculating SK, but it's also possible to calculate S1 through N. What would this be in English language? Probability of what?
Trajectory.
The probability of trajectory. Very good, right? So this is the probability of a trajectory. So it's also possible to compute the full trajectory, which trajectory has the max probability, and that is called Viterbi decoding. Actually, this is probability of trajectory given. Of course, you need the measurements. Okay, so let me just quickly finish by doing one more thing. Yeah, I know it's late, but I think this would be interesting. Sorry, guys. I think this would be interesting and it would finish HMMs. Or maybe we can do this next time. I think it's 11:39, 37 already. Okay, we will do this next time, but this will be application of HMM in another application of HMM in typing on your phone keyboard. You know, when you type on your phone keyboard, your finger is not exactly pressing on the right keys, but your auto edit still figures out what you're trying to type. There is HMM underneath it. And someone just tell me, what is the motion model here? What is your state transition matrix? How do you get that?
Like logical words that you could create in the English language.
Exactly. When the keyboard app on the keyboard software sees that you've pressed a Q, it says there's a very high chance there's a U after this. Right? So that's the motion model, right? You see which characters, which letters are likely to follow which letters, and you have a probability matrix, A to Z, right? Z followed by Y, that probability is very low. Actually, is that very low? No, maybe that's not too low. I mean, there's zygote and all kinds of words where Y follows a Z. Give me two letters that are very unlikely to follow each other.
Z followed
and J.
Huh?
Z followed by Q. Sorry.
Okay, go ahead, Deep. Deep, go ahead first.
Z followed by Q.
Yeah, Z followed by Q. I don't think there's a word that Z is followed by Q. Okay, Eric, you were saying something else?
Just saying Z followed by J.
Z is followed by J, right? JZ. There's no such word, right? So that's your state transition probability. And what's your measurement, guys?
Where they actually clicked.
The location where you measured the finger tap. Now that location may not be exactly at a key. Right? It might be somewhere in between. Like let's say an old man typing or an old woman typing with whose fingers are not precise, like young teenagers who are very nimble and precise, right? So now you have a measurement that is at this location, 1. Is it Q? Is it W? How do you know? That's the measurement given state. And the state given state, previous state, that's the model. You combine, you do auto edit. Right? And we'll also talk about speech recognition, where you're hearing something and you have to decode speech. All of these are beautiful applications of hidden Markov models. Okay. So we'll talk about that next class, but I hope it's clear thus far. Okay, class ends here. I'll hang back if there are questions, but please revisit this. Again, let me tell you, many applications will have hidden Markov models underneath it. Okay. Good. Thank you for staying back so late.
Thank you, Professor.
Thank
Thanks.
you, Professor.
Thanks.
Professor, would you mind scrolling up? I think it was like 1 page, or actually 2 pages.
Sure.
Oh, by the way, is a swipe type keyboard using hidden Markov model as well?
Totally.
I think the swipe keyboard is like pretty genius.
Hidden Markov models, guys. And you are going to do hidden Markov models in your MP with a self-driving car. So yeah, it's coming up. Yeah. So who said scroll up?
Yeah, that was me, but I just wanted to see this. Oh, well, actually, I suppose I kind of have a question. So I understand, like when you were explaining, someone asked about kind of the intuition behind the sum. Like it's basically marginalization, right?
Right.
Usually when we do marginalization, it's not like something like here we see in the example, it's like like PA from PA comma B, but we actually have like a given. We have like probability of something given Sn minus 1. Like how does the given part like tie into the marginalization in our example here?
No, there is no, there's no given. This is PAB. When you sum over B, you get A. This is called the marginal probability.
I get that part,
Hmm.
but if you zoom out a little bit,
Sure.
we have like for beta n minus 1, we have like probability of basically mn given Sn minus 1, or no, above.
This one?
Yeah, like that one pretty much. Because we have mn given Sn comma S minus 1.
Right. Yeah. So ask me the questions.
So it's kind of like, I don't know, maybe I'm just like tripping over the math.
No, don't worry. Get it clear. Yeah.
But like I don't really see how it's like how does the given part not like that dependence doesn't affect the marginalization at all when we sum?
Okay. Let's
kind of take care of it by saying in the next term, like probability of Sn given Sn minus 1, and then
No. Lucas, here is the way to look at it, right? I think all of the confusion starts here, right? Because we do the marginalization here, right?
Right.
So let's look at that slowly. Let's use blue. Let's use a thinner. P of, can you see?
Yes.
Mn given Sn minus 1. This is what we are after. Agreed?
Right.
This is nothing but P of Mn comma Sn minus 1 divided by P of Sn minus 1. You agree?
Yes.
Now, I can write the top part, the numerator, as a marginalization.
Oh, yeah, absolutely.
Then I can write that as P1 by P of Sn minus 1 sigma P of Sn minus 1 Mn, and I marginalize over Sn. I just wrote the numerator as a marginalization.
I see. Okay.
It's exactly this.
Okay. Yep. I see it now. That actually helps a lot.
Good.
That makes sense.
Good.
Because this is the backwards one. So this was forwards, or no, this is backwards. Backwards. So like the position at Sn depends on
still, right? That is fine, right? N is still moving forward. Sn still depends on Sn minus 1.
Oh, right. Because positions, we don't move backwards.
We don't move backwards. Exactly. We don't move.
Okay. Okay. Very cool. Okay. Thank you. That helps. Thanks a lot.
Perfect.
Have a good day.
Okay, you too, you too.
Thank you, Professor.
Thanks, Deep. Thanks.
Thank you, Professor.
Thanks, guys. Okay, I'll stop recording and I'll see you Wednesday.